Okay, good morning. So last time we start this first order circuit and we derive the differential equation for this particular circuit. So we basically consider this very simple circuit having a resistor and a capacitor R and C, and we claim that this particular capacitor has an initial condition of V naught at t equals 0. So what about now? So still the issues there? Okay. Okay, so we basically discussed this very simple circuit. So the speciality here is actually we don't have external sources. We don't have external sources. So the circuit is basically powered by the capacitor, which has a certain amount of stored energy. So the difference here is, so like in the conventional circuit, we don't have any external sources uh, there. So basically the required power is come from the charged capacitor. So then we found that the characteristic or the voltage across the capacitor can be explained using this differential equation. So we found that we can basically model this circuit using this differential equation. So this is a kind of a first order differential equation. First order differential equation. See, so we have first order derivative. So this is the first order derivative. So this is first order derivative. This is basically zeroth order derivative. So if you have the first order derivative as its maximum power, so this becomes a first order circuit. So if you can characterize the voltage or current of a circuit using a first order differential equation, so we then classify this particular circuit as a first order circuit. Okay, so what we basically did here is, once we given a kind of a circuit without these external sources, we just apply Kirchhoff voltage law, Kirchhoff current law, and obtain a kind of a differential equation. So whatever the circuit we discuss here will ended up with a first order differential equation. If you want to analyze the behavior of the voltage or current, so what we can do is we just apply the Kirchhoff law or Kirchhoff laws, either Kirchhoff current law or Kirchhoff voltage law, and obtain a first order differential equation. So once you obtain a first order differential equation, we can claim that particular circuit is a kind of a first order circuit, and by solving this first order differential equation you can easily get the mathematical expression for this whatever the parameters you are interested about. So here we found that we can express this voltage across the capacitor. So V naught e to the power minus T over RC. So this is the expression or the mathematical expression for this ultimate voltage across the capacitor. And once you plot it, we found that, so it's something like that. So we have a time axis. So this is your voltage across the capacitor. So at t equals 0, we have a V naught voltage. So then it's a kind of a decaying function, exponentially decaying function. So this is VCT equals V naught e to the power minus T over RC. And again, we found that this particular value gives the time constant of the circuit, of the RC circuit. So the time constant again, once you map this particular value to the original differential equation, so we found that this RC product is appear here. So it means if you basically explain these coefficients, like here we can map this coefficient A1. So this is A1 and this is A naught. So for this first order differential equation, A1 is basically 1, A naught actually 1 over RC. So then if we basically referring the first order differential equation you obtain here, we can claim that the tau or the time constant of the RC circuit is the reciprocal of the zeroth order derivative coefficient, A naught. So this is equals to RC. So it means like either you can solve it to the last step. Last step means this one, to obtain the time constant, or else if you anyhow obtain a first order differential equation, and you can basically get the time constant by looking at the coefficients of the zeroth order derivative. So these two options are there to obtain the time constant of the circuit. Okay, so then we can do like that. So you are familiar how to evaluate or how to solve this differential equation. So yeah, I guess like in the differential equation module you may discuss this, but yeah.
Sir, some students can't log in with Zoom link.
Sorry, can't log into the. So why it's so? Now already 70 students are there logged into the system. So you can hear me, no? Something. Okay. So anyway, I'll so I'm recording this session, so I'll upload it to the system. So let's update them, like we just try it. What I can do is, anyway, we'll wait a couple of minutes and see whether they can log in. If not, we'll log in to the system again. So until that, I'll explain it. So so this is the differential equation we basically obtained for this particular circuit. So
Hello මේ කට්ටියකට log වෙන්න බැහැ.
okay, then I'll close this meeting session.
Some students can't log in with this link.
Okay, so I'll share the same link again.
So some students can't log in with Zoom link.
Yeah, I'll share the link again.
They have error.
Yeah, I'll share this link. So if somebody can share with the others. So I'll drop a message to your chat box. So just share this link.
Yes, sir, we can hear.
Yeah.
Many students still can't log in with Zoom link.
So I share the link again, so you can just try it. So I drop it to the chat box in the Zoom, so you can copy and paste with your WhatsApp group. Okay, so now like we can rewrite this differential equation. So it's like a1 dvt over dt plus a naught vt equals 0. So this is a generic equation for this first order. So we know that a1 is basically 1. So then it's something like that, dvt over dt plus a naught vt equals 0. So this is the first order differential equation. Okay. So here what happens is, like we don't have any external sources in the circuit. So the so whatever the circuit we discuss here, we don't have any external circuit, external source in the circuit. So what the basically the power or the required power to run the circuit is comes from this initial condition. Okay, so then whatever the output we obtain here, so whatever the output we obtain here is known or defined as the natural response of the circuit. So this is actually the natural response of the circuit. So natural response means the contribution coming from initial conditions. So the natural response is the contribution or the impact due to initial conditions of the circuit. So it's fine. Like, so here we analyze the circuit by assuming that this capacity is charged up to V0 voltage at T equals 0. So then whatever the stored energy of the capacity is releasing through the resistor, and due to that we'll end up with a kind of a voltage response. Okay, so I leave the meeting and relog in it again.